As we saw before the break, the Fourier transform of a windowed sinusoid will look like this. Some temple or mosque or whatever it is, some arch structure. Okay. So there are a few problems with it. First of all, energy is spilling over into frequencies that were not there before. Okay. Wherever it was zero, now it is non-zero. So that is a problem. So we have to somehow get rid of this, or at least reduce the extent. Okay. Now the picture is not complete, because see, this is still calculated at an infinite number of points. Finally, we will be going to a finite number of points on the frequency axis also. Okay. Right now, this axis is continuous. That will also become discrete. But first, this already gives you all this energy leakage. Okay. This is the effect of taking a finite segment of a waveform and then calculating the Fourier transform from there. Okay. Now, one obvious thing is, let's say I take a sinusoid, and in this case I will take some n points. Okay, that's what I have done on the left side, and the result is as you see. And in the other case, I take n1 points where n1 is more than n. Okay, what will happen? I will get something similar to this, but except that because one thing is this is 1 over n1, 2 over n1, and so on. Because of this, the zero crossings are more closely spaced compared to here. Okay, so the first one will be at n1, this one will be at some fraction of that, and then it goes down. Okay, because the zero crossings are closer, there will be more of these things, and it goes down to a lower value compared to this. Okay, so if I plot it on the same axis, and so this height will be different. Okay, so let me normalize it to the same height as this. Okay, this value. So in that case, what it will look like is, first one will be like this, and the second one will be the height of this one. And the third one will be the height of this. The fourth one will be the height of this. Okay. So if you normalize it, you can see that the leakage is smaller if you take more points. Okay. Is this part okay? And this simply comes because this the nulls are more closely spaced, and then you will have more of these lobes as you go further out. So one obvious way of reducing leakage is to increase the number of samples. And this makes intuitive sense also, right? Because we got the ideal result when we had infinite number of samples. Now you take a small number of samples, it is far from ideal. If you take more samples, it may go closer to ideal. That's what you would expect. And as n1 becomes, as n becomes infinity, this height will go up to infinity, which is an impulse. And all of these things will become zero. Okay, which is what you expect. And clearly we can't do that. Okay. But to the extent possible, we can take more and more samples. Okay. So if you take more samples, you will get closer to ideal, which is what you intuitively expect, and which is also what you get from this analysis. Okay. Now what can we do beyond this brute force stuff? Let's say you have taken all the points that you have taken. What is the main problem with this? What are the problems with this? You get, let's say a sinusoid looks like this. What is the problem? A reconstruction, that's not really such a big thing, I think. Also here we just want to analyze what is in the signal. What are all the problems you see with this? Let's say I have two sinusoids. What will be the ideal Fourier transform? Two impulses. So let's say one sinusoid is here, and the other sinusoid is here, and it is smaller. What will be, after windowing, what will it look like? So I have another another of this one. Now, because this has a smaller amplitude, it will be something smaller. Okay, it will something like this. It has to get added to this one. So you may not even realize that there are two sinusoids, because it will look like some smooth stuff like this. You won't even know that there are two sinusoids, whereas it is very obvious from this picture. Okay, so basically the effect of leakage is to mask frequency content in other frequencies. Okay, so that is the problem. Now, how do we go about minimizing it? Let's see. So one thing is increase n, that will work, but there is a limitation. You can't take, like for instance, you buy oscilloscopes. I'm sure many of you have bought maybe from SMDP, maybe from elsewhere, and it says the record length is this much. So that means it can store this many points, right? So there is always that limitation. As technology progresses, maybe you can store more and more points, but you certainly cannot store infinity. And also to work with infinite number of points is a pain, right? The large number of points. It will take more and more time to compute. Okay? So whatever number of points you have, you should do the best job that you can. Any questions so far? Now, like I said, I have not even completed the picture. That I have this part is the black curve here, which is defined for an infinite number of points. Okay. So this is the black stuff. I have windowed it in the time domain. I have taken a finite number of points, but I have still calculated the Fourier transform for an infinite number of points. Now I take samples of the Fourier transform. That is, I will be calculating the Fourier transform only at some points. Okay. I will calculate it at nu equals 1 by 0, 1 by n, 2 by n, and so on. Okay. Let's say I do this. So what will I get? I will get this red point, this red point, this point, and this point, and this point. Right? Okay. So that is the DFT, or the discrete Fourier transform. Discrete Fourier transform is nothing but I take a finite number of samples and I calculate the Fourier transform for a finite number of frequencies. Okay. I calculate the Fourier transform for this k by n, where k varies from, or k by n varies from 0 to half. Okay. And that half is because it's a real signal and it's symmetric. We don't need to look at anything else. Okay. So, is the picture good now? So, if I took the Fourier transform of a sine wave, this is what I would get. Okay, an impulse. And if I take a finite segment of it and calculate it at a finite number of frequencies, this is what I get for the example that I have taken. Now, does this look like a sine wave? Doesn't look anything like a sine wave. In fact, you could equally well say that it is two sine waves. Right? Because these two are at equal. I mean, the way I have chosen it, this peak happens to be between this 2 by n and 3 by n. So, because this is symmetric, the Taj Mahal or whatever the structure, the arch, then these two will be equal. Okay. So, you certainly cannot say it is one sinusoid. In fact, more reasonably, perhaps you can say it is two sinusoids. Okay. So, the leakage has masked other frequency components and you have to minimize leakage. Okay. What can you do? By looking at these pictures, there are two key points here. I will just write it somewhere here. So the first point was that I take the samples of the Fourier transform at k by n, okay, 0, 1 by n, 2 by n and so on. The second key observation that I made earlier, which didn't look very significant then, is the real Fourier transform, the actual Fourier transform is 0 elsewhere, and the Fourier transform of the windowed stuff is 0 at nu naught plus minus k by n. That's because of the zeros in this one. Okay. So, Fourier transform, basically if you take xdf of nu is 0 at nu naught plus minus not k, some other nu naught plus minus L by n. Okay. So we can sort of pretend that at those values it is the ideal value. Okay, at those frequencies it's the ideal value. So now, let's say I had to, is there any sinusoid for which I will get a reasonable answer? For which sinusoid is that? Frequency is multiple of? No, but what you want to happen here in the, see again, these are the things I am doing, right? Because for computational reasons I will compute it only at certain number of points. Fourier transform is computed at k by n. Okay? And from my previous thing I also saw that this is the Fourier transform with the continuous frequency. That happens to be 0 at the frequency of the sinusoid plus minus L by n. Okay? So now, is there some particular nu naught for which I will get the ideal answer? N is sufficiently large. No, it will be approximate. It will still not be ideal, right? You are saying the leakage will become smaller. No, I mean, I am now not changing n at all. Are there some frequencies? If I take sinusoids of those frequencies, will I get a result that is closer to ideal? What is that? Fundamental frequency of which one? Okay, what will be the value of mu naught? Okay, for which I will get a reasonable answer. Just in one example is fine. DC. Okay. Two samples. No, what was that? I didn't understand the second part of what you said. Yeah, DC, it will give you the correct answer. I will show how. Then, what was the second part that you said?
Whatever is there, you can take half by n by 2, n by 2, 2s. One way to complete n by 2, others to complete n by 2. Integer number of based on.
Yeah, but how do we get it from this? What do you want to happen to this picture? That's what I'm. Pardon? No, because see, when I'm not calculating this black curve here, right? I'm not calculating this continuous curve here. I'm calculating only those red samples. So this happens to be, the peak happens to be exactly between these two. So this and this will be equal. So which is it? Is it this or is it this? Perhaps the question itself was not very clear. Let's say wherever nu naught is, I will get.
It will overlap with that point.
I will get something like this. Okay. Now I am going to sample the x-axis only at some points. This one, this one, this one. Okay. So is there some choice of nu naught which will give me a result that looks like this? Huh? Which sample points? It is sampled at k by n, where k by n goes from half to 0. Okay. Huh? You sample it? Basically, see, if nu naught happened to be one of these points where I am going to calculate the DFT, what will happen? The sink-like curve will be reproduced here. Okay. Notice that I am taking points at a spacing of 1 by n. And the sink also has nulls at spacing of 1 by n. Okay. If I have this, what happens? I will be sampling it here. I will be sampling it here, where there is no leakage. Okay. So that's why I showed this as the key points. The XDF is 0 at nu naught plus minus L by n. Okay. So I have to be sampling only at these points. Okay. This k by n that I sample should coincide with this one. Okay. So for instance, let's say, let me redraw this stuff. Let me take two cases. So I will be calculating only at these points. Okay. So let's say this is 1 by 8, 2 by 8, 3 by 8, 4 by 8. I have only 8 points, let's say. Okay. Now, so let me take two cases. Originally, in one case, the sinusoid is here. Ideally, it should be an impulse. But what will I get? I will get this sink-like shape centered at that frequency. The second case, let's say the sinusoid happens to be at 2 by 8. Nu naught is 2 by 8. What will happen now? This will be centered at okay, and I will be sampling only at these points. So here I would have got this one, and this one. What will I get in the lower case? Actually, I think I drew this wrongly also. This will do this. Okay. What are the samples I will get in the lower case? Huh? What is the first sample? 0. I will be sampling only at the nulls, except the peak of the sinusoid. Okay. So because see, the answer I am getting from my MATLAB stuff or any of the numerical stuff is only the blue points. This red thing I have calculated because it was a sine wave and I was able to calculate it. But you will not be seeing this. Okay. So let me redraw the stuff separately. So if nu naught happened to be between these two, 2 by 8 and 3 by 8, which is 5 by 16, and I have taken n to be 8. Okay, that is, I am operating with 8 points. Let's say 8 points are all I can afford. Obviously, you can do more, but for this I will use 8. And in this case, nu naught is 2 by 8 or 1/4. And again, n equals 8. Okay. So what will be the discrete Fourier transforms I will be getting? This is what I get in the first case, and in the second case, I will be getting this. Okay. Which of these two will you believe is a sine wave? Obviously the lower one. Okay. So there is bad news that there is a lot of leakage, but the good news is that there are certain frequencies for which the leakage is 0, because you are sampling only where there is 0 leakage. Okay? And what are those frequencies? What are the good sinusoidal frequencies? What are the values I can give to, what are the frequencies I can have so that I will not have leakage? At least if it is a sinusoid, the spectrum will look like this. Huh?
K into half by n.
K into half by n.
K is the number.
Yeah, okay. Why half by n?
Half is the bit. Half by 1 by n, not half by. K by n.
I am sampling, see, I am calculating the discrete Fourier transform at k by n. Okay. If you place the sinusoid at any one of these points, then the leakage at all the other points will be 0. Okay. Because this spacing is 1 by n. Okay. And this spacing is also 1 by n. Right? Sorry, this spacing is 1 by n. Between the peak and the null of the sink, it is 1 by n. Okay, you think of this as a coincidence. Because you truncated it to n points, you will get some sink-like shape. And there are nulls in that sink. And the nulls are separated by 1 by n. Okay. Now you are also sampling the discrete Fourier transform at intervals of 1 by n. That's what the discrete Fourier transform is. Okay. So basically, the nulls that you get because of the sink must coincide with the points that you calculate. Then you will have 0 leakage. Okay. So the good points, good choices of nu naught are k by n, where k is any integer. Okay. And n is the number of points you are taking. Okay. Is this okay? Is this fine? The sink will have nulls, and you want those nulls to coincide with the frequencies you are calculating, so that you will not be calculating any leakage components. Okay. So if you are using a sinusoid in your spectral analysis, and if you are restricted to n points, you should choose the sinusoidal frequency to be k by n. Okay. Do you want me to go over the whole thing again? Huh? Okay. So this is my signal, and it was probably continuing on as a sinusoid, but I will be taking only the first 8 points. Okay. Okay. Now I construct a signal with these 8 points and all the other points set to 0. Okay. I am not cheating here. I am just trying to see. Previously my definition of Fourier transform had the summation going from 0 to infinity. Okay. So I still have to run it from 0 to infinity. That's why I set the remaining values to 0. Okay. I am not cheating. I am not adding any new information. I am just trying to use the summation. Okay. Now, originally, basically let's say it was a sine wave at this frequency. Okay. And because of this windowing effect, that is because of having taken only 8 points, what I will get will be something of this sort. Okay, this is with respect to the continuous frequency variable. Now, in reality, it is not even this that I am calculating. Okay, what I am calculating are only the values of this at this one, which gave me this, and this one, which is this, and this one, which is a little higher, and here, which is almost the same as this, and finally this. Okay, so this is the X DFT of K. Okay, so when I calculate the DFT, this is what I will be getting. I have taken a finite segment of it. You can think of this imaginary step where you are calculating the ideal Fourier transform at all points and then sampling them at this one. Of course, you are only doing the calculation at these points. Okay, but because of the leakage, this is what you will get. Okay, so going from here to here is the same as going from here to this black curve and sampling the black curve. Okay, so the bottom line is sinusoid doesn't look like a sinusoid, and if I don't get the answers for a sinusoid, which is usually in page 1 of all textbooks, I will probably not get right answers to anything else. Okay, now then I notice that this particular curve, the sink, has nulls at some points. I also see that I will be sampling only at some finite number of points. If these nulls coincided with where I was sampling, then everything would be fine, right? So just let's take an example case where instead of the frequency being here, it was here. Okay, what will happen? This whole this curve will now be centered at this impulse. Okay, then I will be sampling this particular one at here. Sorry, again I drew it wrongly. So sorry about that. So this will be like this. Okay, so I will be sampling it here, 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 and here. Okay, so wherever I am sampling, the leakage is 0. It's not that the leakage is 0 everywhere. I have just shifted the sinusoid around. I have chosen the right sinusoid so that the leakage is 0 where I am sampling on the new axis. Okay, so at least for this, the answer will be something like this. Okay, so which does very much look like a sine wave. Okay, it has a single pulse. Is this okay? So if you are taking DFT of sinusoids, you are taking DFT what is this? So if I am analyzing sinusoids and I am taking DFT with a length n, that is I am taking n samples, then I will get good answers, I will get no leakage. If the sinusoidal frequency is k by n, where k is an integer, okay, and k will be something less than or equal to n by 2 and more than 0. This is because I am only interested in the normalized frequency up to half, right? It's already in the sample domain. Okay? This is okay? So also you see that now let's say I had two sinusoids, and let's say one was here, and so in this particular case if the other one was here, then corresponding to that I will get another something like this, and that will not have any leakage either. Okay, so then clearly I can distinguish the two sinusoids. If I know that they are at integer multiples of 1 by n, then I can clearly distinguish this sinusoid and this one. Okay, whereas before I don't know how many sinusoids this is. Okay, any questions on this? So whenever you are doing spectral analysis with DFT, you should choose, and if you are taking n-point DFT, that's what this is. Okay, I didn't go through the definition of DFT, but DFT is basically the samples, the formula that I showed you. You have n samples, and you calculate the Fourier transform at 1 by n. That is a DFT, discrete Fourier transform, and this is usually available as a FFT command in many packages like MATLAB, and that's what it does. Okay, if you are using sinusoids, then you should choose the sinusoidal frequency to be k by n, where k is an integer and n is the number of points you are taking. Otherwise, you will get leakage. Okay. So, yeah. So now this is the point I will be coming to next. So there are cases where you can choose the sinusoidal frequency. For instance, you are testing an A to D, and what frequency you test it with is up to you. Okay. If it is a little bit here or there, it's okay. So you always choose it so that, and you will acquire the data and decide to take n-point FFT. Okay, where n can be some large number, 2 to the 16 or something. Then you choose the frequency to be some k by n times that frequency. Okay. Now how exactly you do this is by having two signal generators. See, the sampling rate is set by the clock. So your A to D will have the clock input and the signal input. Now the two signal generators which are generating the clock and the signal should be synchronized. Then you will be able to set the frequency to be some ratio like this. Okay. So this is one possibility where you have the freedom of selecting the frequency. The other possibility is where you are just doing analysis, like numerical analysis, when you are doing simulations. Okay. So when you are doing simulation of an A to D, you should also choose it so that it is k by n. That is, what I mean to say is, the normalized frequency is k by n. Okay. So what will be the frequency in real terms in hertz? If the A to D is operating with a frequency fs, okay, and you want to choose some k1 by n, what will be the frequency of this sinusoid? Huh? K by n times fs. Okay. On the discrete frequency axis, it is k by n. Okay, it is normalized to fs. So let's say you have a 100 megahertz sampling rate. Okay. And you have chosen to use a 1024 point DFT. That is n is 1024. Okay. This means that the input frequency can be 1 by 1024 times 100 megahertz. This will be of the order of 100 kilohertz. Okay, not exactly that, but it's basically approximately 100 by 1000. But you should choose this accurately. This ratio should be precise. Okay, or you can choose it to be 2 by 1024 100 megahertz. No, it's not exactly 100 kilohertz. I said it's optimal.
So whatever the number is coming.
Yeah, whatever the number is coming times the. Yeah, exactly. Okay, and similarly, anything up to 512 by 1024 100 megahertz. Okay, this is what you will choose. Now I will show later that not all of these are good choices either for different reasons, but all of these will give you no leakage. Okay, but if you arbitrarily set the signal generator to some value, it could be at, let's say, 3112.5 by 1024. Then you will certainly get signal leakage and you will not be able to distinguish things correctly. Okay. So when you are measuring, this is an important thing when you are measuring A to D converters. Also when you are simulating, because in fact the simulation is a bigger problem. You can't simulate for as many points, right? You have a 100 megahertz A to D, then in 1 second you have 100 million samples. Whereas to simulate for 100 million samples, you put your computer through for a month, it will still not be able to do it. Okay? So it's also even more important in simulation. Maybe in simulation you can simulate your complicated circuit for maybe 1000, 2000 points. So the input frequency has to be chosen correctly. In fact, this is a simple thing but not very well known, or because this is more signal processing related, it's not very well known among circuit designers. So you see a lot of times the FFTs which look like this, which have lots of leakage, and it looks as though there is some quote unquote noise, but it's not noise, it's simply sampling which is done improperly. Okay. So whenever you are simulating or you are measuring in some conditions, you will have the option of choosing the frequencies, and you have to choose it like this. Okay. So are we done? Have we solved the problem of leakage? What else is there to be figured out here? First is frequency may not be known to you. This can happen in many cases because you are getting data out of something and you want to analyze it. Okay, which also you do by sampling and analyzing. Okay, so that is one case where the frequency is not known, and you still have to minimize leakage. So what do you do in that case? What are the other cases where you may have problems? What kind of signal did we apply here? Huh? Sinusoid. So there is no guarantee that the signal will be sinusoid. You could be generating any kind of signal. What do you do in that case? Okay. If it is sinusoids, you can do it like this. It could be some unknown frequency and decidedly non-sinusoidal stuff which you cannot say what the frequency is. It's not a single frequency. Which one? No amount of trial and error will get you there, right? Once you have chosen the number of points, n, these points are fixed, the points at which you compute the DFT. So if your stuff is somewhere here, there is nothing you can do. Okay. Now if it is exactly in the middle, maybe when you double the n, you will hit this point, but it may not be exactly in the middle. So you don't know. But generally, yeah, increasing the number of points helps. But let's say you increased it to the maximum that's possible. What do you do after that? What's that? No. First of all, it may be an output, right? It may not be an input that you apply. It may be an output of some circuit which you have to analyze. Then what do you do? Okay, let's say you have taken 1024 points. Yeah. That's correct. No, that is only for A to D testing. But this is more general than that, right? This is for any analysis of any signals. Okay. So that is one particular thing. And your ADC could have other frequency components, as you will see with the oversampled case. Okay. So I'll give you, although probably most of you don't know about the oversampled case, I'll just give you an example. The oversampled, if you look at the ideal spectral density, it should have your signal and then noise which rises like this. What will happen with leakage here? Let's say the sinusoid is not even there. You try it out without an input signal. The problem is this noise will lead to this, because every one of these components will get convolved with something like this and it will appear here. If the actual thing is something like this, because of this noise and leakage, you may get something here. So you will be measuring more noise. Okay. So for the kind of A to Ds we have seen so far, it is okay, but for oversampled A to Ds, it's not okay. Right? And in this case, it is noise. You don't know the frequency or anything like that. Why does this leakage happen? What was the reason we got the leakage? Truncation, yeah. So, pretty much that thing. So, truncation is what gives you the leakage. right? So we have to somehow take care of that. Again, there is not much time to go into every detail of it, but to quickly summarize, you choose nu naught to be an integer multiple of n, 1 by n, you will get the right answers. Okay. So that's why I said, whenever possible, you use sinusoidal inputs at integer multiples of 1 by n. But we still don't know how to deal with unknown frequencies or unknown type of signals, which are not sinusoids. That's what I think the point he raised, that you may not always know the frequencies. So then there is only one option. You have to somehow reduce leakage. Okay. So what is really happening here? The upper figure shows a signal that is running off to infinity, I mean an infinite number of samples. And the lower figure shows my modification, where I reduce all the samples beyond n to 0. So what happens? There is an abrupt change from here to here. There is a potential for an abrupt change. Okay. The n minus 1 sample happen to be 0, there is no change, but it could be anything, right? So there is an abrupt change. Okay. So that abrupt change, you cannot allow that. So I won't go into the details of it, but all of this leakage is because of that abrupt change. At the two ends, you have an abrupt change here and abrupt change there. Okay. So when you multiply this signal, the upper signal, by a rectangular window, you can get abrupt changes at the boundaries. Okay. If you get abrupt changes at the two boundaries, you can get the lot of spectral leakage. Okay. So I won't go into the details of this, but you know that if you have a step, it will have a Fourier transform magnitude which looks like this. Okay. It has a high DC content and then it goes off, it decays as 1 over f or something. Okay. So what can you do to avoid this abrupt change? Modify the window function. How would you modify it? I mean, what is the general idea? The general idea is to get it smoother. Okay. So you don't want, basically see, it is the window which has that leakage, right? If you look at it, it's the Fourier transform of the window which had all this junk. So this, when you convolve with the sinusoid, appeared around the sinusoid. Okay. So you have to fix the window. The window has abrupt drops at the two ends. Okay. The window has abrupt changes at the two ends. You have to fix that. So what other kind of windows could you use? Some suggestions. Huh? Gaussian. Okay, so there are many choices. I mean, there are lots of windows, but we'll take the most common one. So abruptness is what gives you the frequency leakage or spillage, and you have to use smoother transitions at the window edges. Okay. So one possible candidate is, for instance, you do something like this. Okay. Instead of all of it being uniform, you use a small value here, let's say 0. Okay. Slightly larger value, even larger value, even larger value. Okay. So then it will drop to smaller values. Okay. One possible thing is to use a triangularly weighted stuff. Instead of rectangular, which has abrupt stuff at the ends, you can use triangular ones. Okay. So there are lots of alternatives possible. So one is this, which is very abrupt. Instead of that, you can use something like this. I am showing it as a continuous function, but it's understood that it is sampled. Right? Pardon? Yeah. That's correct. Yeah, deliberately. Yeah. So clearly, the rectangular window modified the signal in some way. Okay, that also modified the signal. Although the shape inside was the same, it introduced abruptness. Now this one is not introducing abruptness, but it's modifying it in some other way. We have to see exactly what the modification is. That's all, right? So if we see that, then we can figure out whether it is acceptable or not. I mean, there are obviously an infinite number of choices for windows, right? We have to see which is acceptable, because we are clearly modifying the signal in some way when we take the finite number of points. Now, right now, our primary goal is to minimize leakage. So if we satisfy that goal and the signal is not corrupted in some way, some profound way, then we'll accept it. Okay? And usually the way to test it is by, you know that the sinusoid, it has to give you an impulse. Now you pass it through different windows and see what it gives you. Okay? So, and we'll see whether the results are acceptable or not. Okay? So, but just to give you a general philosophy behind windows, there is a rectangular window which is quite abrupt. There is a triangular window which is smoother in that the values reduce as you go near the window boundaries, and there you can get even more smoothness. Here it is constant, and you can get something like this that is even smoother, and so on. So there is a huge choice of windows, and then if you go through MATLAB help, you will see. So firstly there is the triangular window, and then there are some other windows known as the Hann window and the Hamming window and Blackman and so on. Okay. Now there is not enough time to go through the actual Fourier transform for all of these. I'll just briefly discuss the Hann window, which is a very good window in that for most general cases it reduces the leakage to acceptable levels, and certainly in our delta sigma work we use the Hann window whenever we are simulating. Okay. Now it will have some other effects which also I will discuss but not derive. I will just tell you what it is. Right? So there are lots of windows, and the philosophy is to get smoother boundaries. Okay. Now normally we think of ourselves as not using any window, but okay, we are really using a rectangular window because we are simply taking a finite number of points. Okay. The first one was rectangular window, and we know now in some detail what it does. The other thing I will discuss is the Hann window. Okay. Before this, just a couple of points about the discrete Fourier transform. DFT stands for the discrete Fourier transform, and it's given by the formula I had shown earlier. It is calculated at discrete points k. Some n, you calculate the summation from 0 to n minus 1, and this is weighted by e to the minus j 2 pi n times k by n. Okay. So you are calculating it at normalized frequencies k by n. Okay. So that is the discrete Fourier transform. And normally you hear the term FFT, which is the fast Fourier transform. Basically it's a way of calculating the discrete Fourier transform in a fast way, computationally. Okay, that's all. So although you say about taking FFT, you are really taking a DFT, and there is some algorithm which makes it fast. And the most optimal, now this how fast it is depends on n. Okay. And the most optimal values are integer powers of 2, it turns out. Okay. So let me not make this n. So this n should be some 2 to the m. Okay. So that's why normally you take maybe 8 FFT or 128 FFT or 1024 FFT, which are integer powers of 2. But you can take other points also. It may just be very slow. In fact, you can see, you can take maybe just for the heck of it, you take 16384.50 in MATLAB, which corresponds to 2 to the 14. And you take 16383, which is actually one less, but this will be much slower than this. Okay. So that's because the algorithm doesn't work very efficiently when it's not an integer power of 2. So I recommend taking an integer power of 2 usually, but it's not necessary, like I said. Okay, you can take it for other points also. But I'll work all my examples with integer powers of 2. Okay, because I don't want to go on saying if n is odd, n is even, and so on. I'll assume that it's some integer power of 2, which means that it is even. Okay. And what is the Hann window? If you are taking an endpoint FFT, I'll take small n, obviously. So here I have taken n equals 8. The Hann window is given by 1 plus cos 2 pi. So this is WH of n 2 pi times n by n. Okay, sorry, 1 minus, not 1 plus. Okay. And this is for n going from 0 to n minus 1. And it is 0 outside of that. Okay. Because we still have to limit ourselves to n points. Okay. The rectangular window was constant between 0 and n minus 1 and 0 outside. This follows some complicated shape between 0 and n minus 1 and it is 0 outside. So what is the value at n equals 0? What is the value at n equals 0? Huh? What is cos 0? 0, 1. So here it is 0. Okay, at least one condition is satisfied, that at one boundary it is 0. And then it follows the sinusoidal type of shape. It will do this and this. And it reaches a maximum at 4. So roughly speaking, it will look like this. Okay. What is the n equals 4? What is the value? Huh? 1? What is the value of the cosine at n equals 4? This cosine? This lowercase n equals 4. Huh? Cos pi? What is cos pi? Minus 1. So this is minus 1. So you get 1 minus minus 1, which is 2. Okay. And then it comes down. Okay. This is fine. Now it's important to note that the last point is not 0. Okay. Now I won't go into the reasons why that is so, but that's how it is. And if you calculated this is 0 and this is n minus 1. And if you calculated the nth point, it would be 0. Okay. So the last point is not 0. So it starts from 0 and ends at something close to 0, but not 0. Okay. And if you calculate the next point, it would have been 0. That's how the Hann window is defined. Okay. And this is available with the command. If you want to compute this wave, for n points. In MATLAB, you would use Hann, the number of points n that you want to take the DFT for, and you have to use an argument called periodic. Okay, this makes sure that the last point is not 0, but the next point is 0. Okay, so I will give you some examples which you can hopefully work out in MATLAB, but this is the Hann window that you have to use in MATLAB. Okay. So you multiply it by cos, and it roughly follows the intuitive things that we had been saying, that it weights the boundaries less compared to the middle. Okay, that's the basic idea of windowing. Now, what will happen if you pass a sinusoid through a Hann window? So we don't have time to calculate it, I'll just give you the answer. First of all, the rectangular window had a Fourier transform like this. Okay, that's what it looks like. The Hann window, it turns out, will have a Fourier transform something like this. Okay, so is it better or worse? Huh? Better. Better or worse? That's exactly what happens. So if you want to see very close to 0, it is inferior. So let's say the sinusoid was here in the middle, again at some wrong frequency. What will the rectangular window do? It will give you something like this. Okay, this is slightly higher. Sorry, I used consistent colors here. The rectangular window would have done something like this, and the Hann window will do this. Okay. So what happens is, right next to the sinusoids, it is much worse. Okay, but away from the sinusoid, the energy is much less. This you can see by plotting it on a log scale or a dB scale. Okay. So right next to the sinusoid it is much worse, but far away from the sinusoid it is much better. So that is the trade-off. It turns out that there will always be this trade-off. If you make the window better for higher frequencies so that the leakage energy reduces, just around the sinusoid you will always get a lot of leakage. Okay. What does it mean? What does it imply for the practical case? Let me now place the sinusoid on one of the good bins for the rectangular window. Okay, let's say the sinusoid was here. Okay, coincident with this. The rectangular window would have given a Fourier transform like this. And when I sample it, I will get 1 here, 0, 0, not 1, n by 2 here, 0, 0, 0 and so on. Okay. So in fact, I will get when the frequency is accurately set, I will get the ideal result with the rectangular window. What will I get with the Hann window? Okay. I will get this and this. And after that everything will be 0. Okay. So in fact, if you have a single sinusoid placed on the bin, one of the bins, these are known as bins, placed on the frequency k by n, you will get 3 non-zero points, whereas you will get only 1 non-zero point with the rectangular window. So that non-ideality is there. Even when it is accurately placed, you still get 3 points. But what does it mean? That means that if you had one sinusoid here and another sinusoid here, you certainly cannot distinguish it with the Hann window. But if you have one here and another smaller one here, you can do a much better job with the hand window than with the rectangular window. Okay? So it trades off this is known as the main lobe size. The main lobe, it gets broader, but far away it is not interfering. Okay? It keeps its own house perhaps dirty, but it's not putting garbage into other people's place. Whereas the rectangular window, yeah, it is very compact and nice, but it's throwing a lot of garbage elsewhere. Okay? So that's the trade-off. And there are even other windows like the Blackman-Kaiser window, which is much wider here, but the energy drops off even more quickly. Okay? If you see a basic signal processing textbook like Oppenheim and Schaefer, you will have plots of all of these things. Right? So that is the trade-off. You will always get these 3 points with the hand window, but far away from it, you will get a much better performance. Okay? So this means that the resolution is limited. With the rectangular window, in the best case, you can place sinusoids in 2 bins next to each other and distinguish between them, whereas with the hand window, that's not possible. Okay? So any questions on this? Yeah.
We don't modify the amplitude of these samples.
That's correct.
But with these other windows, the amplitude of samples get modified.
That's correct. So that effect is described by this convolution. When we have a rectangular window, we are convolving it with this. When we have a hand window, we are convolving it with this. So the entire effect is described by this one. Okay. Now, the one thing is, yeah, it looks like it is being modified, but this is what it means. That it is getting convolved with something like this. Okay. Now, there is one small problem that you can't tell the absolute value of the amplitude by looking at the DFT. But usually you are interested in the ratio of 2 things. So that will be accurate whether you use the hand window or the other one. Okay. So when you use the hand window, to get a measure of the signal, if you have a sinusoidal thing, you have to sum these 3 values. Okay. Not the values of the DFT, but you have to do a root mean square sum. Okay. Let's say this is 1, 2, 3. Should take x3 square plus x2 square plus x1 square. Okay. That will be the mean square value of the signal. So there is some modification, but that modification is described by this convolution. So there is more leakage from the neighboring bin, but much less leakage from faraway bins. Okay. The rectangular window, because it is 1, it looks like it is not modifying it, but because of the abruptness, it is modifying it a lot in some other sense. Okay.
Now, this hand window, what are the other things?
Yeah.
And you can implement it in
Pardon?
you can implement it in
No, these are usually used only for analysis, right? For instance, if you want to analyze the data coming out of an A to D, you still get the samples that you get. And this multiplication by hand window and all that is happening in MATLAB or whichever software you use to analyze.
So, that doesn't have any actual implication?
No, it does, right? Because it is able to reduce the leakage.
You pass your data to this window.
Yeah.
In what kind of analyzing all this stuff?
No, you will be windowing your data, right? Or I didn't get your question. What is the...
So that's you have this signal.
Yeah. Yeah.
And sample data and then passing through the window, the kind of either rectangle.
That's correct. Yeah.
So what I'm asking is how do you realize this window?
The window is realized in whichever tool you are using to analyze. For instance, let's say you are measuring an A to D converter. Okay. You will be taking some number of samples. Let's say 1024 samples out of your A to D. Okay. You can just take those 1024 samples and take the DFT as it is. That is one possibility. The second thing is you multiply it by this particular function with n set to 1024. Okay, you take your 1024 samples and multiply it by this one. So that is, you are passing it through the hand window. And then you take the DFT. So, but the multiplication and all that will happen in the post-processing tool. Okay. It's not something you have to implement into the A to D because it's very easy to analyze it. There is no point wasting that hardware trying to implement it. Okay. Similarly, when you simulate, you get the samples, you have the simulation and analysis, yeah. Simulation and analysis. Now there is one other thing where it is useful in that when you are designing FIR filters, digital filters, it's also used, but we won't go into that. As far as we are concerned, it's a data analysis tool. Just like the FFT is a data analysis tool, right? You want to see the frequency content and you have to do the windowing also. Okay? So the bottom line is you will get these 3 points in the Hann window, and if you look at MATLAB's help or signal processing tools, you will get the actual Fourier transform of this, and it will explain to you very well what's happening. So I thought you can try some of these things as an exercise because it's quite easy to do and it's much more vivid when you see it yourself. Okay. So the first one has to do with this DFT and windowing and so on. I'm assuming you will use MATLAB, but anyone here who does not have access to MATLAB? Well, everyone has access to MATLAB, so I don't have to worry about it. But there are other things like Octave and Scilab which you can use for similar purpose, and these are free actually. Let's say you define T to be 0 to 8191. Okay, basically my N is 8192. This is what it means. I am taking a large number which is also a realistically large number, right? Then you take cos 2 pi f naught t. You define this to be some vector. Okay. V1 is A1 cos 2 pi f naught t. And you can set A1 to be whatever you want. Let's say 1. In this case, you can even do it to be 1. Okay. And you take the FFT of this. Let me define V1f to be the FFT of V1. Okay. And plot. Huh? Oh, is it? Sorry. Okay. I didn't realize it was cut off. Okay. And you can plot (20 log 10) of the absolute value of V1f. So it's important to take the absolute value because this itself is a complex number. It can be a complex number. And you take 20 log 10, I mean, it's a dB measure. The usual reason for taking a logarithmic measure is to distinguish between very large and very small quantities. Okay. If you have some component which is 1 and another component which is 1 by 100, on a linear scale it's very hard to find. Whereas with a log scale, even if it is 1 and other is 1 by 1 million, you will still be able to find it. Okay. So you can plot this. Just play around with f0. So for instance, you can take f0 to be 1 by 8192, or let's say 3 by 8192, or let's say 5, 1 by 8192, things like that. Okay. And you can try also f0 is 1.5 by 8192, 3.5 by 8192, 511.5 by 8192. So it's a small change in frequency. That's the point, right? But you can see how the FFT behaves and it will become very clear. Like however much I say here, it's much more obvious when you do it yourself. Okay. So you can do this, try this out. And also you can try A and B with multiplied by Hann window. Okay. You define a Hann window for 8192 points, but please do remember to use the periodic argument. Okay. You use Hann 8192 periodic, and then you multiply your V1 with the Hann window, and you take the FFT of that and do the same thing. Repeat the exercise with that. The first one without doing anything is like using the rectangular window. Okay. Now doing that is like using the Hann window. Okay. So the DFT is calculating the Fourier transform on these frequencies, some k by 8192, right? And in the first case, in A, the frequencies are coincident with this, and in the second case they are not. So you will very clearly see what the effects are. Okay. And also when you take the Hann window here, you should see what happens. This is already on the pin, on the FFT pin at the good frequencies. But still you will see some leakage because of the Hann window. Right? At 2 points you will certainly see a leakage. But you will see which is better for what. Okay, whether Hann window is good for this or that. And so on. Okay? Is this clear? So please try it out. It's not, if you are even slightly familiar with MATLAB, it will not take you more than half an hour to do all of this stuff. And you can play around with different things and see. And one other interesting exercise is, you take something 2 pi f1 t plus a2 cos 2 pi f2 t, and let's take a1 to be 1 and a2 to be, let's say, 0.01 or something, or 0.001, something very small. Okay. Again you can try f1 to be on the bins. Okay. Or you can also try f1 to be 1.5 by 8192. And you can pretty much choose f2 to be anything you want. You can also try f2 on and off the bins. And see, you have one large signal and one small signal. Okay. In fact, you can make this even 0.001 also. First of all, if I plot it in the time domain, yeah. 3.5. This is 3.5. But you can try 4.5 also. Basically, see, these things are of the form k by n. These things are not of the form k by n. That is the main point. Okay. Now, if I have, let's say, 0.01, and if I plot a sinusoid, even if the 0.01 I can't make out in the time domain, right? If I have a sinusoid and a small harmonic content on top of it, I will not be able to make out at all, small different frequency content. But in the frequency domain you can, because you have the logarithmic scale, you can even distinguish something that is 1 volt and something that is 1 microvolt. That is the other advantage of frequency domain. Okay? It separates the frequencies and you can distinguish widely varying strengths. Now you can see in both cases, when f1 is k by n and f1 is not k by n, how your distinguishing ability will change. Okay, that's the point of this exercise, because the whole point of going to frequency domain is to be able to easily distinguish between the two, because in time domain you can't. But because you don't take the DFT properly, your ability to do that may be compromised. So this is extremely important if you have to do any data converter design at all, because for simulation and measurement you need this, and if you don't do this properly, you will not be able to figure out anything from the DFTs and FFTs. Okay. Any questions so far on Hann window, DFTs, all of this? So even if you simulate or measure a simple flash converter or any complicated converter, you will have to do this. Okay. And this is also useful in simulation of not only of A to D converters, because in simulation everything is sampled, right? You will take samples and if you want to find a distortion of an amplifier, what would you do in simulation? Let's say you build an amplifier and you want to measure its distortion. What will you do? you will have to check the strength at each one, or use this dot Fourier analysis which is available, which is basically the same thing. It is doing FFT and checking the strengths. Approximately it is doing the same stuff. Okay. So essentially what will happen is, you have an amplifier. Let's say it's a gain of K. So if the input is X, the output should be Kx. But in addition to this, usually you will also have these nonlinear components. Okay? What will be the result of this? If you put in a sinusoid, what will you get? Harmonics. This will give you second harmonics, and this will give you third harmonic, and so on. Okay? Now how will you simulate this? Because in simulation you still have to sample this and take an FFT. Okay, this is not a hardware block, but effectively this is what you will have to do. Okay? So you have to do exactly the same thing. Let's say you choose to do endpoint FFT. Okay? The input signal frequency endpoint FFT with sampled at TS. Okay, that is this. Of course, you have a lot of freedom in simulation, but let's say you decide that you will take 8192 point FFT sampled at 100 nanosecond intervals. Okay. So you will have to choose the input frequency so that it is some K by 8192, not this K. Okay, let me not make this. The gain is A naught or A, let's say this is A. So K by 8192, where K is an integer. Okay. So then you will be able to distinguish everything cleanly. Okay. So this is also important for simulation. Again, you can try this also in MATLAB. You simply have some x which is a sinusoid. You pass it through a1x plus a2x square plus a3x cube and take the DFT of that. And again you can see what happens if you have it on the bin, off the bin, and so on. Okay. Now there is one more point about choosing K. Right now I said any integer is okay. It will be on the good places. It will be in the good places. Okay. Okay. Now, for instance, let me take K to be n by 4. In this case, 1024. Okay. N is 8192. Right? What will happen? My input will be at Fs by 4. Okay. What will be my outputs? What will be the fundamental output? Where will it be? If I had an ideal amplifier, where will the output be? If I pass the sinusoid through an ideal amplifier, what will be the frequency of the output? Same, right? It will be exactly the same. Ideally, this is all you will get. What will happen in reality? You will get distortion. So where will be the second harmonic? Fs by 2. Where will be the third harmonic? Fs by 4, and so on. Now for data analysis, this is sampled. What will happen because of that? This is sampled at Fs. This is the amplifier output. This is sampled at Fs. So what will you see in the DFT? You will see the signal peak at Fs by 4. You will see a peak at Fs by 2. What will happen to the 3 Fs by 4? it will alias to Fs by 4. What will happen to fourth harmonic? It will alias to DC. So you will only get this. Your harmonic has fallen on top of your original signal, so you can't find out the strength of the third harmonic from this. Okay? So what do you have to do? So now you are taking an n-point DFT, right? You are taking 8192 point DFT, but it's useless. Everything is 0 except these points. Okay? Whereas with 8192 points, you will be able to get 4097 different points. So ideally, you should be able to get this much. Okay? So what was wrong here? You have chosen it such that the harmonics fall on top of the original. There are these problems. Okay? Ideally, we should be able to distinguish if you take an n-point DFT, n by 2 different components. Okay? So what should you do here? What is the fix? Let's say this is fixed. You are still taking 8192 point DFT sampled at 100 nanoseconds. What is the thing you can fix here? Huh? Value of k. Yeah. So how will you choose it? I have chosen it to be n by 4. Okay. I still want the input frequency to be close to this because the performance of the amplifier may be sensitive to the input frequency. I want it to be close to this, but not necessarily exactly this. So what will I choose? What is the possible value? N by 3? No, that may not even be in this form, right? Because 8192 by 3 is not an integer. Okay. It has to be of the form k by n, but I can't choose k to be n by 4. Okay, what will I choose? I can't choose k to be 1024 by 8192. So what is the close thing that I can choose? I mean, something what is the closest thing to this that is possible? Huh? Fs by 2. No, that is very far, right? That is 2048 by 819. Actually, I made a mistake. This is 2048, not 1024, but that's a small thing. See, what are the allowable frequencies? K by n, where k is an integer. So what is the nearest allowable frequency to this? N is 8192. What is the nearest allowable thing possible? Nearest possible thing? Huh? Yeah. So the closest thing is you take the next of the previous integer. You take 2047 by 8192, which is very close to this, or 2049 by 8192. Okay. So let me evaluate the harmonic explicitly and show you. So let's say Fn, let's say the fundamental, second, third, fourth and so on. So originally I was at 2048 by 8192 or 1 by 4 Fs. Where will be the second harmonic? 1 by 2. And this will be at 3 by 4, which will get alias to 1 by 4. This will be at 1, which will get alias to 0. Okay, and fifth one will be 5 by 4, which will get alias to 1 by 4. Okay. Now let me choose the very slightly different frequency. Okay. Where will be the second harmonic? This will be 4094 by 8192. The third harmonic? Six one four one, right? Okay, and where will this alias to? 2051 by 8192. Okay. It will be very close to this, but not exactly same as that. That is the point. Okay. Whereas here, this is exactly the same as that one. So by making it very slightly separate, see, I am not changing the test in any fundamental way. Because let's say my Fs was 1 by 100 nanosecond, that is 10 megahertz. Okay. And 1/4 of that is 2.5 megahertz. Now this is also very, very close to 2.5 megahertz. So it's not like, okay, if I originally had 2.5 megahertz and now I test it with 100 kilohertz, yeah, it's a totally different performance. But I still have something very close to what I want to test, but I have taken care that the harmonics don't alias on top of each other. Okay. 2051. Similarly, the fourth harmonic will be at, this will basically alias to 4 by 8192. It's not going to go to 0. Okay. And similarly, the next one will be 2047 minus 8, 2039 by 8192 or something. It will be separate. You can be guaranteed. Okay. So what is the thing you should do? You should choose it properly. I mean, properly meaning basically the technical term is that you should choose k by n, where k is mutually prime to n. Basically, k and n should not have any common factors. And n is very commonly equal to some integer power of 2. What are the factors of this? What are the factors of 2 to the m? Just 2, that's all, right? 2 repeated so many times. So if you choose k odd, that's it. If you have an odd number, 2 is not a factor of that, and that's the end of it. Okay? So you choose k odd. Although any k by n will result in no leakage, if you want to get rid of, if you also would want to avoid the possibility of harmonics aliasing on top of each other, you should choose k odd. Okay? That is one other detail that you have to include. Okay? So this again you can try with an example. So let's say you try, your amplifier has a characteristic 1 times x plus 0.01 times x square plus 0.01 times x cube plus, you can take as many terms as you want, x to the 4 and so on. And you take x to be a sine wave as before. Okay? And you can try various things, like f1 to be 1 by 8192, you can take f1 to be whatever, 2047 or 2048 or 2049 divided by 8192 and see the results. Okay. You can again also try, let's say 2047.5 by 8192 and see what happens. Will you be able to distinguish the harmonics or not? Okay. So these are all things you can quickly try and find out. Any questions so far? I think this will help you whenever you design A to D or simulate it, it will help you measure it in a way. And again, this whole exercise will not take you more than half a day. In one afternoon, you should be able to check everything very easily, even if you are not familiar with MATLAB. Okay. Any questions? So that's about analysis. So we did spend a lot of time on this stuff, but this is very important if you have to design anything at all. I think Shanthi will in the afternoon talk about some oversample, or he'll continue with the flash, and there is time he'll get to the oversample stuff. And like we mentioned yesterday, a lot of the oversample stuff is covered in that course as well as in the tutorial, so you can go through that as well. Okay. Anything else that you would like to discuss now? So dynamic errors of the A to D. Okay. So what will happen is, so let's say we have a sinusoidal input to an A to D. Okay. At the output you would expect the sinusoid plus some quantization noise. Okay. In reality what will happen is, it will have harmonics and it may have some other tones which are even non-harmonics, and it will have quantization noise. Okay. So the method of measurement is still the same. You apply a sinusoid so that its frequency falls in, its frequency is one of these good frequencies, and then you take the samples and you take the DFT. Okay. So let's say you take the DFT and you plot it. You can clearly identify the harmonics and non-harmonic components and so on when you have chosen K to be odd. Okay. So that is basically how you measure it. Now what does it mean? So just like you do for an amplifier, first of all, there are distortion parameters. Okay. Typically the second and third harmonic are most important. So you measure HD2, which is basically 20 log 10 of the fundamental, or the second harmonic divided by the fundamental, and similarly HD3 is 20 log 10 third harmonic by the fundamental. Okay. So this is exactly as you do in an amplifier, except that these numbers come from the DFT. Okay, these numbers come from the FFT. Now there is also something known as the signal to noise and distortion ratio, SNDR. Okay. For this, what you calculate is basically 10 log 10 of the fundamental signal square divided by sum of everything else squared. Okay. Everything excluding the fundamental. Basically you find the energy in every bin, you add it up, and you take the ratio of the fundamental to that one. So that is the signal to noise plus distortion. Okay. And sometimes you omit the DC because DC offset is not important, but you include everything else. Okay. Which one? In this one? No. Because the noise, it has a lot of bins. Okay. Maybe the strength is small, but you have a lot of noise bins. Okay. So you will, this will be certainly less than either of them. Okay. So this is only distortion. This is distortion and noise. And there is another measure which is basically the signal to noise ratio. Which is 10 log 10, the square of the fundamental divided by square of the other things. In this case, you exclude the fundamental and the harmonics. Okay, anything that you can identify as harmonics, you exclude, and this is how you get the signal to noise ratio. Okay. So you have noise, you have distortion, you have noise plus distortion. You take the signal, ratio of signal to all of them and then specify. Because each one matters in different cases. That's how you do this. But all of this comes from the DFT, and that's why taking the DFT is properly is very important. Pardon? No, it generally doesn't matter. Because the way you choose it if you choose the signal frequency to be some k by n, and it will go through different phases in every clock cycle, so it's not such a big thing. So that should not be important. So especially see, when you take n to be a reasonably large number, when you have n as very small, then the phase will be important, because let's say you have a sinusoid and then you sample it only at 4 points. Okay, here, here, here and here. So this is one possibility, and another possibility is here, here, here and here. So the signals are very different now. But when you have a large number, this is not going to happen. Okay, so you will get points everywhere, whether you take the phase to be slightly different or not. Okay, so that's why phase is not a very important thing, as long as you have a reasonably large n. Anything else? Now one last thing, which again something that I talked about yesterday, which you can easily simulate in MATLAB, is also this quantization error. Okay, so let's say you take V1 to be a cos or sine, it doesn't matter, and you can choose similar values as before. So t goes from 0 to 8191, so that you have 8192 points, and f goes from f is, let's say, 1 by 8192 or something. Okay, it doesn't matter which one you choose. Let's say you do this, and let's say you call this the ADC output. You simply say, you round this off, okay, and you take A to be some relatively small number, let's say 128 or something, okay, and then you round it off, and you take a quantization error, which is V1 minus VADC, or the other way around, and you plot the histogram of this with proper intervals. Okay, what will be the maximum value of E in this case and the minimum value of E? For this particular example, what is the maximum value of E? What is the minimum value of E? Why 1 by 128? Is it dependent on A or is it dependent on the quantizer? Depends on the... What is the LSB of this ADC? What is the LSB of this ADC? No. Why? Why are you looking at the amplitude? Where is the ADC happening? Which of these statements? 1, 2, 3, 4. Where is the ADC action? I mean, quantizer action, not ADC. Actually, this is not ADC exactly, quantizer. Which of the statements describes the quantizer? Second one. Okay. So, there, what is the least count? LSB. So, round means it rounds it to the nearest integer. So, the step is 1. And the error is between plus half and minus half. Okay. So, this will be... This is okay. This is not dependent on A. Right? So, you plot the histogram of E. What will you see? You will see values between minus half and half. And you take the histogram interval to be some small number like 0.05 or something smaller, so that you will see, again in MATLAB you can see this. And you can see if it is really uniform or not. Because yesterday I said the quantization distribution is uniform. From this you can easily figure out if it is uniform or not. Okay. Similarly, you can take the FFT of the quantization error and see if it is white or what happens, etc. Okay. Is that okay? Any other questions? I think we can stop here. If you have anything else, we can discuss it before going to lunch.